Recently, we learned about freezing point depression, where you add a non-volatile solute to a solution, and that lowers its freezing point. In this lesson, we're going to learn about a related process called boiling point elevation, where we add a non-volatile solute to a solution and it actually raises its boiling point. A common example of that is putting salt in water. Let's take a look. So perhaps we are making spaghetti, and before we boil the water, we add a bunch of salt to it, and that will actually increase the boiling point of that solution and allow us to cook our spaghetti at a higher temperature. Okay, how does this process work? Well, anytime we add a non-volatile solute to a solution, it will increase its boiling point. So non-volatile just means that it's not prone to evaporate. And in this case, our solute that we're adding is sodium chloride, which is a good example of a non-volatile solute. Ionic compounds have really strong forces holding them together, and so that makes them non-volatile. And then the solution that we were looking at here was our salt water. The expression that we use to calculate the change in boiling point looks really similar to our expression for the change in freezing point. Change in temperature, that is the boiling point elevation, is equal to Kb times molality. Again, this concentration of molality is in terms of moles of solute over kilograms of solvent. Again, we're not going to actually calculate molality in this lesson, but we are going to take a close look at calculating boiling point elevation when given the molality. Okay, so that change in temperature there is an increase of our boiling point. And it depends on both the molality of our solution and the boiling point elevation constant, which is Kb, which is very similar to our Kf for our freezing point depression. All right, now, once I've gotten the change in boiling point, I may want to actually calculate the new boiling point. How does that work? Well, because boiling point elevation increases the temperature, we're going to start with our original boiling point and we're going to add that change in temperature because it's an increase. And then we'll be able to find our new elevated boiling point. Let's do a quick example of that. So let's say that I have water, which normally boils at 100 degrees Celsius. The boiling point is increased by 4.5 degrees Celsius by the addition of salt. What's its new boiling point? Well, there, all we're going to do is take our original boiling point of 100 degrees Celsius, and we're going to add to it our boiling point elevation of 4.5, and we're going to get a new higher boiling point of 104.5 degrees Celsius. So that's the new temperature our water would boil at by the addition of salt. Let's take a look at two specific examples here of how we can calculate the boiling point elevation and the new boiling point. This problem looks at benzene, which is an organic solvent. It typically boils at 80 degrees Celsius, and we're told its Kb is 2.53 degrees Celsius kilograms per mole. Kind of some weird units here that just make our equation work out so that when we multiply concentration and molality by our molality, we just get out degrees Celsius. And then it wants to know what's the new boiling point, the elevated boiling point of benzene containing 1.2 in terms of molality of a non-volatile solute. So that italicized M, it means molality. And basically here, we're going to follow the same steps we did for our freezing point depression. We're going to identify the variables given. Always a good thing to do when we start a problem. And the variables given here are our original boiling point, which is 80 degrees Celsius. And it gives us the Kb, which is the boiling point elevation constant. And we're told that that's 2.53 degrees Celsius kilograms per mole. Lastly, we're told the concentration of our solution in molality, which is 1.2 mole. All right, now step 2 is calculate that boiling point elevation. We're going to calculate delta T with our boiling point elevation equation, and all we have to do there is multiply our Kb times our molality. So that's the two parts there. So we have our Kb and our molality. Delta T is equal to Kb, which is 2.53, times molality, which in this case is 1.2. And when we multiply 2.53 by 1.2, we're going to get 3.036 degrees Celsius. Now, we're not going to round that for sig figs until the very end. Always a good rule, only round at the end of your problem. Lastly, we're going to want to add delta T to the normal boiling point to get our new elevated boiling point. So that's step 3. Remember that our original boiling point was 80 degrees Celsius. And then we're going to add to that our elevation of 3.036 degrees Celsius. That's going to give me 83 0.036. And now we'll round for sig figs. In the problem, I'm given the concentration of 1.2 in terms of molality. That has 2 sig figs. So I'm going to round this to 2 sig figs, and I'm going to get that my new boiling point is 83 degrees Celsius. So we can see that I've increased the temperature at which that benzene boils by 3 degrees Celsius by adding this non-volatile solute. Let's do one more example. Here we're told that water typically boils at 100 degrees Celsius and has a Kb of 0.512 degrees Celsius kilograms per mole. What is the boiling point of a solution with a concentration of 2.20 in terms of molality? And in this solution, we actually have sugar water. So sugar turns out also to be a non-volatile solute that we can use to adjust the boiling point. All right, first of all, identify the variables given, just like we did before. The first thing we're given is the boiling point of water, which is 100 degrees Celsius. Awesome. Okay, then we're given the Kb, which is the boiling point elevation constant, which turns out to be 0.512 degrees Celsius kilograms per mole. Also awesome. Now, we're also and lastly told the concentration, which in terms of molality is 2.20. Okay, well, let's go to step 2 then and calculate that change in boiling point. The change in boiling point is equal to Kb, 0.512, times my molality, which is 2.2. And when I multiply those two together, I'm going to get 1.1264 degrees Celsius. Again, we're not going to round for sig figs until the very end. And in step 3, we're going to calculate that new boiling point by taking our original boiling point of 100 degrees Celsius and then adding, because we're elevating the boiling point, 1.1264 degrees. And when I add those two together, I'm going to get 101.1264 degrees Celsius. And then when I think about sig figs, I'll realize that my concentration, my Kb, and my temperature are going to have 3 sig figs, and that means I'm going to round to 3 sig figs, which would be 101 degrees Celsius. All right, 101 degrees Celsius. That is my new boiling point of my water after adding sugar to it.